it will be the most enormous map of the universe ever made. There's been this invisible universe there all along. We've seen the tip of the iceberg, and LSST is going to show us a lot more of that iceberg.
What's the ultimate limit to what you can do? Let's try to do that. You want to head there from the start, otherwise you've sold out right from the beginning. It's 20 years. When you add in the operations, LSST is over $1 billion. You don't devote that time and that money to something that isn't pushing the state of the art. Historically, it was called LSST, Large Synoptic Survey Telescope. The term synoptic has been used in astronomy to mean regular, but the word actually comes from synopsis, and it means of the whole. So in that sense, Large Synoptic Survey is the survey of everything. All the ideas, basically, for large field of view systems involve 3 mirrors. You need 3 mirrors. The camera will be the largest electronic camera ever built for astronomy. It's the size of like a small truck.
There will be an education and public outreach program disseminating LSST data to the whole world, and that all of the scientific data products will be completely public and equally accessible to everyone in the United States who is a scientist and all Chilean scientists.
LSST is extremely challenging technically. The challenge on the telescope is to get what we call a large field of view, which means that a single picture has to be a big angular part of the sky. For LSST, that field of view is about 10 square degrees, which is roughly 40 times the size of the full moon. So if you imagine looking up at the sky at the full moon, and drawing a circle that's 40 times bigger than that, that's one LSST picture. We do that every 15 seconds. You know, we're doing 10 square degrees at a time. We tend to do 2 15-second exposures and then step to another place. So every 30 seconds or so, we're taking this enormous telescope and moving it a lot. We don't have time to sort of wait for the whole thing to settle down so we can take the next picture. We want to just bang, 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 one picture after the other. So the telescope had to be very stiff. It's 3.2 billion pixels make up the camera. So remember, a given exposure is about 15 seconds, and we close the shutter. You don't want to spend a lot of time with the shutter closed because you're wasting the night, basically, doing that. So if you're going to do 15 seconds of basic exposure, we decided we needed to read out the whole camera in 2 seconds. LSST will generate something like 15 to 20 terabytes of data per night. Over the 10 years, when you include in all the auxiliary information that comes from the processing, we're expecting that the LSST database will be a few hundred petabytes. A petabyte is 10 to the 15 bytes. You know, storing that may seem daunting. That's not really the problem. The problem is finding anything in it. Okay, you can shove everything in your closet. The trick isn't shoving it in the closet. The trick is finding it.
And this question of finding the needles in the haystack is one that's not just interesting to astronomers, but has also proven interesting to statisticians and computer scientists.
Part of LSST is to, you know, take pictures at different times and then compare those pictures with previous pictures or the archive of previous pictures of that part of the sky, and then alert that, something's changed.
Different collaborations around the world might develop their own, you know, brokering service or filtering service to take in the whole stream of 10 million alerts and allow users to apply their own way of slicing and dicing the data to just pick out the small number of unique things that would be interesting to them.
And because a lot of things happen in astronomy on pretty fast timescales, we set a requirement for ourselves that we would issue an alert within 60 seconds of closing the shutter. So the telescope and camera are on this mountain in Chile. Close the shutter. Within 60 seconds, we have to get all those data down through Chile, all the way up to the United States, into the data center in Illinois. We need to analyze that image, compare it to a reference image of the same part of the sky, detect everything that's changed, make a catalog of that, and alert the world to it within 60 seconds. We will issue 10 million of those per night. 10 million per night. The reason we're trying to do that is the science demands it. It's pushing the state of the art in every area. It will be a great experiment, and maybe fundamental new discoveries will come from it, maybe it won't, but just having built the thing will be an accomplishment into itself. This could be one of the greatest scientific experiments in human history. It has the potential for that, because it touches everything from the solar system to stars to the galaxy to the expansion of the universe itself. One experiment that gathers all those data.